Hello, everybody. I'm Xander Hill. I'm that fellow right there. I've been at Plaid for 3.5 years. I've been every sort of manager that you could have other than a VP. So I was a manager of a team, a manager of managers, and a tech lead manager for the online storage team that I founded while I was a manager of managers. I've now moved back to my roots, and I'm a principal software engineer inside the team. And with that, I would like to introduce my colleague here who took over, Andrew Chen, who is our new engineering manager from the team itself. I'm eternally grateful to him. So to get to our story about how we've accelerated adoption at Plaid, we'll talk about Plaid's backstory. We'll talk about our technical landscape. We'll talk about why we moved to TiDB, how we transition a single service, what some of our learnings are, and also how we're accelerating the process. That's a lot to cover, so we'll dive straight in. Our story at Plaid started off in 2012 when our co-founders, Zach and William, were doing a hackathon, and they were building out a personal financial management tool. They quickly became frustrated with how difficult it was in order to integrate into financial institutions in the United States. Many of them didn't have APIs at the time. So they instead decided to focus on building an infrastructure layer that would make it possible for other individuals and developers in the community to iterate on financial services and build them out. So at this point, we've got 12,000 financial institutions in the United States, Canada, and Europe that we're integrated into. We have 8,000 different high-quality applications that are out there. You might recognize some of them as Venmo, Robinhood, PayPal. And we've also started to integrate into the enterprise side of things with Microsoft, Verizon, and Google. We have about 1,000 staff members in the company. We took $734 million of funding total. Our last funding round was in 2021 with a Series D when we were valued at $13.4 billion. All of that sounds great and impressive and wonderful on stage, but also it means that on the platform engineering side of things, there's never a good time for downtime, and the company keeps scaling rapidly. Our technical landscape on the storage side at Plaid when I joined was we didn't have a storage team at all, but I solved that part. And what we have at Plaid for online storage is about 800 database servers, about a total of 500,000 QPS, 650 terabytes of total on-disk size, and we're targeting internal SLAs of at least 4 nines of availability. When you break that out into what is the SQL-based portion of our stack, that's about 450 database servers, about 140,000 QPS, about 40 terabytes of data in size, and still the same SLA requirements. We've started to move a number of our workloads over onto TiDB. So if you go into the subset of that is TiDB specific that we're already operating over there right now, we're running about 160 database servers that are TiDB servers, about 20,000 QPS, 20 terabytes of on-disk size, and that constitutes about 700 vCPUs in the clusters. We have our target that we will be fully moved off of AWS Aurora by mid-2025 for every single MySQL workload that we have internally. We've passed the Rubicon where we are no longer admitting new services directly onto AWS Aurora. They go straight onto TiDB with a self-service offering internally with our self-hosted TiDB cluster and the enterprise support contract. The topology that we decided to go with is we have a multi-tenancy scenario. You'll hear a lot about multi-tenancy today at the conference. It's what made sense for us both from an operational effort side of things and also for the availability guarantees that we need to offer our internal customers. So we broke out our production clusters. We have 3 production clusters. We broke them out into a tier 0 service cluster, a tier 1 service cluster, and a tier everything else service cluster, each with their own specific SLAs. We are using resource groups and query limits very heavily internally to try to isolate the effect of one noisy neighbor against another. We're still pretty early in the experience of using resource groups, but so far we've seen them be valuable and something worth dialing in further in our own production systems. We run 3 non-production clusters. One of them is valuable enough to talk about in the presentation, which is that we have a full production style cluster that we use for the validation process of making sure that our query plans are good, that our load patterns are good when we're shifting traffic over from AWS Aurora over to TiDB. Which brings us to why are we doing a 2-year project and why are we moving to TiDB. So it comes down to three things on our side. The first was reliability at scale, the next is our developer velocity, and the last one is the maintenance burden that we are experiencing on the existing system. We do have a pretty small team. It's 6 engineers and 1 manager. Maintaining reliability at scale for 300 MySQL clusters was a fair bit of work. It also meant that we were forced to do upgrades because it was a hosted platform on a timeline that was not of our own choosing. We found that at a certain point of scale on the AWS Aurora platform that we were on, we started to hit limits where we were unable to easily offer teams further right scaling, difficulty on the developer velocity side with them being able to properly make online schema changes in larger tables. I'm defining larger tables here on that platform as anything like in the 2 to 10 terabyte for a single high throughput table. So we would instead give them the horrible advice from the database side of saying, don't make the schema changes on that. It's not safe. It will never complete, and it will degrade your performance. And yes, we can spend a couple weeks assisting you trying to use PTOSC, trying to use Ghost to make these changes. But we still found scenarios where we were unable to succeed at that. And so having engineering teams that had to work around throughput limitations on the right pathway for AWS Aurora meant that engineering teams at Plaid were spending like 1 or 2 engineer years every year working around the limitations, re-architecting things to deal with performance problems. Lastly was the amount of effort that we were spending on maintaining those clusters. They are a managed service, but they are not a set and entirely forget service. So doing the upgrade pathways on those from 5.6 to 5.7 took us about 2.5 engineer quarters of the full engineering online storage team working on upgrades to get from 5.6 to 5.7 in a safe manner. So moving forward from there, we predicted that our reliability gains on TiDB, and we validated these in early processes so far, are going to come from 2 main factors. One of the factors is scaling operations happening in a non-disruptive way. So we no longer need to take clusters offline for a couple minutes at a time to do resizes, cluster configuration changes, those sorts of things. And generally, planned maintenance on it. We've been able to do planned maintenance on the TiDB side in a way that allows us not to take downtime. Moving on from there, so we had come out of the 5.6 to 5.7 upgrade process. We knew what we were facing with the 5.7 to 8.0 upgrade process that would be mandated very shortly. And we knew that it would be an even bigger task than what we had faced previously because of compatibility changes. So if we were going to go through that style of very high effort for the migration, we wanted to make sure that we had step function level improvements with the tooling and the offering that we were able to make internally to our client teams. Not an incremental change that we saw we would have gotten with MySQL 8.0. So a key thing we were looking for was horizontal scalability. We assessed the engineer effort and the maintenance burden that we would take on if we were to create a custom in-house sharding solution that would be generalized across all of the 300 clusters that we run internally for MySQL. So that was incredibly important to us to make sure that we could get through those write throughput limitations with horizontal sharding, and also to reduce the impact of single node failures. Next was targeting the node downtime maintenance. So we wanted to make sure that we could do configuration changes, node resizes, any like scale outs of the cluster. All of those should be dynamic and shouldn't need maintenance windows. They shouldn't even really need to notify client teams of that kind of stuff, except as a nice courtesy FYI. We also felt pretty bad about telling people they couldn't make online schema changes to their tables, and wanted to make sure that was a possible capability on larger tables. As secondary factors, cost savings was an important consideration for us, and going with a multi-tenancy architecture allowed us to make that true. We were really looking for simpler rolling upgrades in this process. The tooling provided, so we're using EC2 and self-hosted and then an enterprise contract. The tooling that were provided via tie-up, once you get some of the tunings in place and the configuration values, we've been able to make those upgrades in place and with only about a week of effort, which is a massive improvement compared to the 2 engineer quarters plus that it took our team to do the AWS Aurora upgrades. Cool, so Where are we at in our process? We started this in Q1 of 2023. We were reviewing our options. We discovered TiDB and PingCap at that point. We reviewed the ecosystem for other tools. We completed a proof of concept in Q2 with one of our tier 0 services to make sure that the query patterns coming out of that one would be well supported by a distributed database like this. Q3 was all about writing an RFC, securing the financial buy-in, securing the business and organization and headcount buy-in, and the organizational planning for the next year and a half of effort. Q3 and Q4 was about building out infrastructure internally to be able to support a comparable offering so that there was never a degraded experience for client teams. They got to go straight from a mature platform on AWS Aurora to a early but still mature platform on self-hosted TiDB. We adopted our first service in production in Q1 of 2024 this year, and we've now moved 17 services over. We've been told that this is a very aggressive timeline to move that many services that quickly across disparate workloads, but we also don't care. We're doing our best to complete it in a rapid fashion. We have 9 other services in progress. We're down for our tier 2 and below services and our simple tier 1s. We're at the point where we can do a single service in 1 engineer week with the 200 steps that are necessary and the 20 runbooks that are necessary to execute. And that means we're targeting a total of 41 services by the end of the year. The feedback we've gotten so far about the rigor and the procedures that we have, especially from people that we respect a lot for their own technical depth, is humbling. So this is a quote from Ed Huang, one of the co-founders of PingCap, that Plaid has migrated more services within a tighter timeline than nearly any customer we have had. It's been nothing short of a pleasure to partner together. And with that, I'll hand over to Andrew to explain some of how we're achieving this on a macro level.
Thanks, Sander. I'll now walk us through how we migrate a single service from MySQL to TiDB. So like Sander mentioned, there are over 200 steps and 20 runbook executions, but at a high level, there are 4 steps. So identifying and fixing incompatibilities, setting up the TiDB infrastructure, validating both performance and correctness, and then performing the switchover. I'll go into more depth in each of these, into each of these steps. So in many cases, there might not actually be any incompatibilities to fix, but there are a few to call out. The following is a non-comprehensive list, but does include the incompatibilities that we've encountered most often. So the first is primary keys. Plaid requires that tables moving on to TiDB have a primary key. The reason for this is because TiCDC does not support replicating correctly for tables without a primary key. So we use TiCDC to replicate to our downstream MySQL fallback cluster. So if our client teams have tables without a primary key, we ask that they add one with a simple schema migration. Next is foreign keys. Plaid does not support foreign keys on TiDB. Foreign keys may have performance issues for distributed databases and are also not compatible with some of the tooling that we use, like data migration, for example, that we also use for replication. So if our client teams have foreign keys as part of their tables, we ask that they drop these constraints from the database and instead move these checks to the application layer. TiDB also does not support the serializable transaction isolation level. So our solution for this is to work with our client teams to understand their use case for serializable and figure out a way to continue to support their use case or meet their requirements using a lower isolation level, and potentially this means making some application changes. Last, we have auto-increment IDs. So TiDB does support auto-increment IDs, but they behave slightly differently compared with MySQL. So specifically, auto-increment IDs in TiDB are not guaranteed to be monotonically increasing at the cluster level. Imagine we have 3 TiDB nodes, each with an ID range. So 0 to 3,000, 3,000 to 6,000, 6,000 to 9,000. Depending on which of these nodes you hit and in which order, you might get out of order IDs. So this might not matter much if your application doesn't depend on the ordering of these IDs, but for our client teams that do depend on this ordering, we ask that they sort by a timestamp column instead. The storage team at Plaid is responsible for identifying these incompatibilities, but we rely on our application teams to actually fix these incompatibilities because they're most familiar with the application logic, and best understand how these changes might impact their service. So after these incompatibilities are addressed, we move on to actually setting up the TiDB infrastructure. So what this looks like is we take an S3 snapshot of the original MySQL database. We then import this into TiDB using TiDB Lightning. We'll then set up a clone of the original MySQL database using that same snapshot for rollback purposes. And then we'll set up replication between these three databases such that they're kept in sync with a little bit of replication lag. We'll also make some changes to the application. So we'll integrate the service with our blue, green, red migration client such that we're able to swap traffic between these three databases using feature flags transparently under the hood. And as we're performing these setup steps, we're also validating at each step of the way. So when we're importing data using TiDB Lightning, we're verifying that the data is still consistent afterwards. When we set up DM replication or CDC replication, we verify that these replication steps are actually working correctly and the data is still consistent. Using these validation steps, we've been able to catch a few issues primarily with binary primary keys and timestamp columns. So these have caused a few issues for us in terms of data consistency, but we've been able to work with PingCap to identify solutions to all of the issues that we've encountered so far. So we've been very grateful for their help. Aside from validating that the ecosystem tools are working correctly, we also leverage dual reads and dual writes, validating that live traffic is both performant and returns the correct results when executing against TiDB. Leveraging this validation step, we've been able to identify some performance regression. So more recently, with one of our tier 0 high throughput services, we found a query that was running perfectly fine on MySQL using the correct index, but when replayed against TiDB would not use the correct index and had a performance regression. So because we were able to leverage dual reads and writes to catch this issue before the actual switchover, we were able to fix it before it became a much bigger issue. So this leads me into the switchover itself. So to perform the actual switchover, we'll flip a series of feature flags. The first one is to turn off traffic to the writer. We'll then let binlog replication propagate all the way through to TiDB, at which point we'll flip a second feature flag to swap traffic over. We'll wait for the feature flag values to propagate, and then we will flip a third feature flag to re-enable traffic to the writer. So at this point, all traffic should be live and all traffic should be on TiDB. In terms of the impact this will have, readers should stay online the entire time, so there should be no downtime to the reader. Traffic to the writer might have downtime up to 2 minutes, but in many cases, we've gotten this down to less than 60 seconds because of the process improvements and tooling that we built out. And you might be wondering, why do we not do gradual switchovers with shadow traffic? The reason is because it's very difficult to maintain data consistency between two live databases that are constantly changing. So we've made the intentional decision to go with the atomic switchover approach in order to not deal with the data consistency issues. And lastly, if we experience any issues during the switchover, we always have the option to fall back to our standby MySQL cluster. We haven't actually had to use this so far, but it's still a really nice guardrail to have and is a form to mitigate risk. And now I'll pass it back over to Xander to talk more about our learnings and acceleration process.
Awesome. Thank you, Andrew. So we're all here in the platform layer of engineering or infrastructure, and what that means is that we're going to start off by focusing on the what didn't go well kind of things before we move into the other fluff. So as far as the not going quite so well, we have had some issues with different open source ecosystem tooling provided by PingCap, particularly when we're working with binary primary keys, either in the where clauses or other parts of the query. And that's been in some of the importing process, the replication process. That's definitely slowed us down, but each time we've discovered them, we've identified it, we've flagged it for PingCap as a vendor, and worked through and had very quick patches out of them in order to be able to unblock us and move forward. Next up on challenges that we've had, timeline estimation inaccuracies. So we did set a very ambitious goal for the project that was that we would be completed with all of our services, all of our 300 MySQL clusters by the end of 2024. We are going to be about 25% over that in our total final estimation of what we're able to achieve, which is that it's mid next year. So it's good, but it's not great. One of the things that factored into that on our side is trying to make the estimates far ahead of time at the very beginning of the project when we hadn't yet moved a number of our harder tier 0 services. That combined with some of the tooling challenges that set us back definitely contributed to 25% over budget on the timeline. The last part of it on the timeline part is the building out the offline ETL and making it exactly feature compatible with what previously had out of the AWS Aurora side has been more effort. I attribute some of that to our team not having the proficiency at the beginning with how those internal tools are set up and being able to swap in place without any disruption to internal clients. Something that Andrew mentioned was the query plan differences. We've been fortunate enough to catch those mostly in our validation clusters, but we're now guarding ourselves against that better through resource controls and resource isolation patterns. We also have some SEV intervention tools that will help us if we do see those start to crop up. But you need to make sure that you're validating all of your traffic before you switch it over to TiDB if you want to avoid dealing with that in prod and fixing forward. On the more positive side of things, we've seen a number of the choices for why we chose TiDB be validated in practice and operated in anger. So rolling upgrades, we were able to execute that with about a week of total preparation time and a single day of going through and executing the upgrades on all of those 6 clusters. We have been able to go back to these teams that we said we can't offer you online schema changes, it's not safe on your table size, you just can't do it, to say, no, actually you can do it now and you don't really need us for it. Just submit it for review, we'll take a look and make sure it still looks okay, and then it'll be processed by the database. We've been very fortunate with our client team engagement and with having a good reputation internally that makes it easier to collaborate there. We've decided to Terraform everything because we're using EC2 and tie-up, and that's been incredibly valuable. If anyone needs a fork of the MySQL provider for Terraform, we are currently hosting one of those, and that has access to things related to resource controls, resource groups, query limits, any of that that you would want to make part of your automatic definitions as you spin up new services. Multi-tenancy has gone generally well. It's not simple, but it works. So if you're going to roll out multi-tenancy, make sure that you're thinking very deeply through the resource controls and how you're doing resource isolation within your clusters and making sure that you're also, to the greatest degree possible, isolating workloads into more homogeneous settings for comparable workloads. We've also been very happy with tie-up, so thank you, Ed. And last in the going well but entirely unexpected category is the runbook automation. So I'll talk about that on the next slide. We started off this project like most companies might by writing very long Google Docs of every single step in the process of everything we were doing. So we had 200 steps, 20 runbooks to do for a single service transition. And we quickly realized that wasn't scalable in a few different aspects. So one way that it's not scalable is it's very difficult to keep people up to date on the team and the best practices of what you're doing with runbooks when they've copied them from a Google document or maybe are keeping their own Google document of part of the process. The next piece of it is that it's not scalable to recreate those manually every time and change all of the parameters correctly. There's a lot of introduction for human error there. So what we ended up doing, I talked to a colleague from another company and found a solution because I'd rather reinvent someone else's solution than do something net new, and spent a weekend inventing how we would do dynamic runbooks. So what they are, they're an open source CLI that allows us to create them with kind of a standard template. It also allows us to clone them and auto-clone them based on the parameters that we already know related to the service that we're transitioning and what destination cluster it's going to and the TiDB side, things like that. So we can auto-plan these with good defaults. And what they really are at the end of the day is a Jupyter notebook wrapped in a lot of layers of hundreds of or thousands of lines of SDK. So we're using Dino's TypeScript kernel for all of the code inside of them. It means that instead of having tens of pages for a single runbook that's in Google Docs, instead we have a very short Jupyter notebook that abstracts it down to the core steps of what they are in a human relatable way. And then they're executable code that you run through and you see the validations and it's posted to Slack to show, did this succeed, did this fail, all the time stamping that you want. That means that we can abstract away the concepts in our system and not think about the details of them. So thinking about things at the abstraction level of, oh, I know that I'm using this Aurora cluster and I am transferring from that Aurora cluster over to this specific TiDB cluster. Great, those are the only two parameters I need to know other than the environment. And that means we can parameterize the runbook. We can then instantiate those as default template steps and then have the operator of the runbook power through it in a very fast way. It's been able to get us from the point where some of these service transitions might take a couple weeks down to a few of them, like I mentioned earlier, being able to get under a week of engineering effort, despite running all those 200 steps. And when you look at the total scale that we're looking at of about 100 services and each one needs 200 steps, that starts to be a lot of steps to get right manually for a team of 7. So it unifies the effort of 7 engineers into a codified source of truth. It allows us to iterate quickly and make those feedback changes into the system itself that's then pulled from source code for anyone that's building their next runbook. It massively reduces our human error for correct parameters, the way we do permissioning, the way we handle security aspects of secure secrets and making sure that those are transient in the execution environment. They've been a huge game changer for us. So on the more thematic process of the things that are speeding us up, first, I attribute a lot of our success in the process to working on some of the hardest services early. In H1 of 2024, we moved from a tier 2 service to a tier 1 service to a tier 0 service, all in the same 6-month span. And that allowed us to figure out some of the truly harder things that don't show up until you're working in your higher throughput tier 0s. It allows us to de-risk more of the total project timeline. Next up is we realized that when you're doing 100 services, you need to start thinking globally about the optimum efficiency, not at a local level of a single service transition. So we started off by outsourcing more of the steps to the client teams, and then realized that we were gaining speed where they were not gaining speed, and decided to instead internalize those parts of the process. And the storage team now takes over something like 95% or more of the process for transitioning a service. We include the client team at the beginning. We include the client team in consultations on the way. If we find incompatibilities, we work with them so that they can resolve it. And then we include them in the cutover process. It also ends up reducing the dependencies that we have on client team timelines, staffing, all of that, which helps us iterate faster. We've started to batch together routine steps, so you'll notice if there are 200 steps to do an individual service and you have 100 of them, there are some things that can be batched together that mean that you have a lot less context shifting to do if you can tackle them with a single engineer over a couple days, rather than every time that you do a service starting from scratch and running it all the way through. It improves our correctness of outcomes. It simplifies what's needed for that individual service transition engineer. And we're starting in the H2 of this year to start to see the gains from that and recommend that you adopt it in your own procedures. Next is we've standardized everything that we can, and things that are non-standard are the enemy of our progress. So decisions, database drivers, rollback procedures. We've saved redundant efforts because engineers at Plaid have a strong culture of standardization. So we already had a single database driver that was used for most of everything. That's where we were able to inject the behavior related to feature flags and traffic shifting. We have standardized naming for our projects, for our feature flags, for feature flag creation, for procedures on how we transition a service, the decision framework, on what consistency guarantees we offer depending on what tier a service is. And all of that enables us to reduce the cognitive load in what we're doing along the way so that we can focus on the individual steps. Bringing it all back to a single slide of the more tactical parts, Tackle your hardest stuff early, see something, then do it, then automate it, then iterate on those automations and feed them back to your team. Make sure you have a unified interface. Maybe that's your proxy SQL layer, maybe that's your TiDB proxy layer, maybe that's your database driver, standard library. Standardize everything and stand by those until you can come up with a better option. Use dual reads and dual writes to make sure that you have correctness and performance correctness before you start to shift traffic onto your production clusters. Otherwise, you will also find that occasionally query planning doesn't go the way that you would expect from AWS Aurora. Always be ready to fall back even after you've done your final cutover. We maintain our fail-forward clusters for another 2 or 3 weeks past the point of our final cutover, depending on criticality. A more like meta and touchy-feely point is maintain morale. You're on a 2 or 2.5 year project. You need to maintain morale inside your team. You need to make sure that there's a strong vision of how you're improving things. You need to make sure that that vision is clear to the other client teams inside the organization. And you need to make sure that that's clear to the org and the executive sponsors. So share your learning, share your wins, share the times that you're able to migrate schema changes without having production problems, share the fact that it only took you a week to do your rolling production cluster upgrades instead of the 2+ quarters before. And lastly, I strongly encourage you to automate your cutovers and rollbacks. We get like pre-check analysis and live polling to make sure that we're clear to go ahead, and then we have clear color-coded signals to indicate, yes, you're clear to proceed to the next step, or no, you're blocked from it and you can't proceed on this cutover, and go back and figure out why. That's been able to reduce our cutover timings from what we initially thought might take us 4 or 5 minutes down to, in the shortest case, 43 seconds. With that, thank you everybody for joining our process. I hope we've been able to help you in yours. Thank you.